Okay, welcome back for part two of the problems of the lesson from section 5.4. First lesson, I know there was a lot to it. It's all about the fundamental theorem. And if there's ever a problem set that I hope that I get questions, whether through email or whatever, that I can address through email or make a video or two for solutions, this is probably it. Because again, there's a lot of different types of things that you're expected to do. The next topics involve mean value theorem and average value of a function. Now, I'm going to give an example of this in a minute, but I first want to get to a picture as usual. The mean value theorem basically is another one of those existence theorems. We had a mean value theorem for differentiation, and that basically meant that the slope of a tangent would be slope the same as the slope of a secant at some point. We call that point C. The mean value theorem for integration is similar, that there has to be a C value so that the integral from a to b is going to be the value of the function at that c times b minus a. Well, what does this really mean? Well, here would be a picture. Let's say I have some function from a to b. And that function could go up and down, but basically it looks like this. That's the function from a to b. Well, this part of the function, the integral of f of x from a to b, is basically this area. So that would be that purple area. The mean value theorem basically says there has to be a c value somewhere between a and b so that f of c, which is basically the height of that value, times b minus a is equal to that area. And what it really means is that there has to be a height, so to speak, that if this could float from the bottom orange to the top orange, somewhere in there is the exact area. So I basically make this irregular purple area into a nice rectangular area. So let's just say it happens to be about right here. That point along the x-axis is that c value that we're looking for. So that's basically what the mean value theorem says. Average value of the function is really where it starts to happen, because the average value of the function is that f of c. And if we take this and solve for f of c, we can see that if I just divide by b minus a, I have it. So the average value of this function would be this type of a picture. Now here's an example. What if you were asked to find the average rain in April? Or the average amount of rain in April? Or maybe this, how about the average temperature in April? Well, we could find the average high temperatures in April very simply by finding all the high temperatures divided by 30. We could find the average low temperatures the same way. But if I want the average temperature, I would have to find all the temperatures. Well, how many temperatures are there? There's an infinite number. So if I could have a temperature function, somehow graph that, I can basically find the average temperature by doing this very thing. We could do it numerically also, but that's one of the examples of using the average value of a function. In any case, let's look at one that's more purely based on just the mathematics and functions. We want to find the average value of 3x squared minus 2x from 1 to 4. So I could graph it. What I'm basically doing, at 1, this is going to be at 1. At 4, it's going to be much larger. It's up at 40. We could find its vertex simply by finding the derivative, setting that equal to 0. The vertex of this parabola would be at 3. Is that right? That didn't seem to make sense. Okay, so this thing is going to dip down, and at 3 would be the smallest number. In any case, it's some type of a parabola. Okay? So we want to find the average value of this function. In order to do that, I'm basically going to realize that the average value is nothing more than the integral, which is 1 to 4, 3x squared minus 2x dx. And then I'm really going to divide that by this difference, b minus a, or multiply it by 1/3 if you want to think of it that way. So the average value of the function would be 1/3. This would be x cubed minus x squared from 1 to 4. That's going to be 1/3. 4 cubed is 64 minus 16 is 48. Minus, that's basically 0. And so you get 16. So wherever 16 is, that would be the average value. So the area of that rectangle would be the same as the area under that curve from 1 to 4. That's an example of average value of a function. The second big topic, or the really last big topic of this chapter or section, is something known as the second fundamental theorem. Now, the second fundamental theorem, again, for our purposes, we just have to be able to use the second fundamental theorem. Some of the applications will be more evident in future courses. But basically, we can have functions that are already integrals. In other words, this function is defined to be an integral. And so what if I want to differentiate it? Well, remember, integration and differentiation are kind of opposite procedures. Whatever this integral does to f of t, if I differentiate it, it's going to undo it. So the derivative of this capital F is basically this original function. Now, there are a couple requirements. This lower limit must be a constant. And this, of course, is your variable. So let's look at an example of it. Let's say I want to find the derivative of this integral. And again, they kind of cancel each other out, but do they really? One option would be to find this integral, put these two numbers in, evaluate it, and then find the derivative. But because I can recognize that this is a setup for the second fundamental theorem, this is a constant. All I need to do is put an x where the t is, and I get the square root of x squared plus 1. Might seem a little magical, but let's take a look at another one before we decide on that one. Here, what I should do to get the derivative, again, that's a constant, so it does apply. I just need to put that x cubed where the t is. The only thing is that's not enough. In differentiation, the chain rule would require me to multiply it by 3x squared. Because that's the derivative of this number that I put in. Now let's take a closer look at that and why that has to be true. Let's go about and do this a little bit different way. I'm going to actually find this integral. Because I can. Up here I couldn't. You can try, but you can't. Here I'm going to find this integral. Well, the integral of cosine is sine. So that whole thing is basically saying f of x is the sine of t from pi to x cubed. Well, that's just the sine of x cubed minus the sine of pi, based on our fundamental theorem. So again, that's my capital F function. Well, if I now want the derivative, I'm going to take the derivative of sine x cubed, which is cosine x cubed, times 3x squared, minus the derivative of sine of pi. Well, that's just a constant. That's 0. you can see these are the same thing. So that pretty much wraps up a very quick outline of some of the big topics from section 5.4. The fundamental theorem helps us evaluate these definite integrals. We can use that in what we call accumulation problems. Anytime we want to find an area or we want to sum an infinite number of things together, we need integration. A very popular type of application that comes from that is this idea of the average value of the function, which is just really rewriting the mean value theorem. It's really trying to find what is the average height of a function. So if I were to take some irregular area and turn it into a rectangle, what's the height of that rectangle? It's almost like this purple thing here is ice, and if it would melt, how high would that be if it was in this container? And then finally we have this thing known as the second fundamental theorem. It's basically used whenever we have a function that is defined as an integral and we want to differentiate it. Well, of course, differentiating an integral, they should kind of undo each other. It'd be like taking something and squaring it, then turning around and taking the square root. You're back to the beginning. So if we have an integral and we want to differentiate it, we should just be able to go back to what the function is. And in many cases that's true unless the number that you put into the function has a derivative itself. Then there's kind of a hidden chain rule going on when you're finding the derivative. If you can first integrate, like we did here in the purple, and then differentiate, that's fine. Problem like this, though, that's not possible because that first step of first integrating can't be done, at least with what we know. So there you have it. Once again, if you have any questions as you're working through this problem set from 5.4 over the next several days, even through next Monday, please let me know, and I'll set up a couple videos on some solutions because I know there should be some questions here because there's a lot going on. If we can take care of this problem set, I think the rest of the course just kind of flows from this. So good luck with this. Enjoy your long weekend, and I hope everything goes well. And we'll get back with you on Monday.